Great day to one and all. I am Mr. Kim J.C. Ensho, and today I will be discussing with you this introduction to inferential statistics. So I hope that you are with me, and I hope that you will be learning also something from this session. So probably some of you have heard of what we call the normal curve or your normal distribution. The standard normal distribution is, if you could see here, is in fact a bell-shaped curve, which is actually defined by this f of x as this function. And if you could see here in the x-axis, we have here the z-scores. So here we have 0, and you go from, if you go to the left, we have -1, -2, -3 z-scores, and so on. And you could have here 1, 2, 3, and so on. And in the y-axis here, it actually represents the probabilities. It is a symmetrical bell-shaped curve representing the probability density function of a normal distribution. The area of a vertical section of the curve represents the probability that the random variable lies between the values which delimit the section. And here are some of the properties of your normal curve or of your normal distribution. The normal distribution curve is in fact bell-shaped. So it's like this. And the mean, median, and mode are all equal and are located at the center of your distribution. So if you have here, we have here your mu or your mean. And it so happened that this line here, for example, this particular part where the mean is located, it is also the same as your median and as your mode. The normal distribution curve is unimodal, meaning to say there's a single mode. That's why if you could see here, there is only one peak, and this is where your mode could be found as well. The curve is symmetrical about the mean. When we speak about symmetrical, for example, if you will fold this graph, if you will fold it along this line, then the left portion and the right portion will in fact coincide with one another. And the curve is continuous as well. So if you could see, this here, portion here, could actually continue until infinity, going to the left, and this one continues infinitely going to the right. The curve never touches the x-axis. In other words, this curve is in fact asymptotic. So this goes on forever, but will never touch this horizontal axis. So it's asymptotic, forever going near and near, but will never touch. And the total area under the normal distribution curve is equal to 1 or 100%. Why? Because the maximum, and remember, area of a certain event is from 0 to 1. So the maximum, the lowest possible probability is 0, meaning to say that event will never happen or is impossible to happen. And the highest probability is 1, and that event will surely happen. This one here, since it's a probability distribution curve, then all the probabilities here, the area under this curve is in fact equal to 1, which means to say that if you have this line here, if you cut it here, then the area of the left, at the left, is 50% or 0.5, and the area here at the right is also 50% or 0.5. So this is your normal distribution. There are two types of means and standard deviations. But before I proceed to that, I forgot to tell you that in here, you have your mean here, and as you go to the left, you are actually subtracting your standard deviation. So you see, your mean is mu, your standard deviation is this sigma. If you go to the left, you subtract the standard deviation or sigma. So we have here u minus sigma. If you subtract by sigma again, it will become u minus 2 sigma. Then subtract again, you have u minus 3 sigma and so on. But as you go to the right, you are adding sigma or standard deviation. So you have mu plus sigma here, plus sigma again will be mu plus 2 sigma, mu plus 3 sigma, and so on. You could still have here mu minus 4 sigma and so on. You could have here mu plus 4 sigma here and so on. Remember, this continues forever. However, the probabilities here after this and going this part here, they are just actually very small. There are two types of means and standard deviations. The mean and standard deviation from the probability distribution function, denoted by mu and sigma respectively, are what we call parameters. The mean and standard deviation from a sample, denoted by x bar, and small letter s, are what we call statistic. A statistic and a parameter are related, but actually they are not the same thing. These are both mean and standard deviations, but this one is called parameter. This is population mean and population standard deviation. And from the sample, we have here your x bar and s. In what way are they different? We will know later on. For now, let's have the 68, 95, and the 99.7 rule for normal distributions. For normal distributions, 68% of the area under the curve, if we say AUC, that means area under the curve, is within plus minus 1 standard deviation of your mu or population mean. 95% of the area under the curve is within plus minus 2 standard deviations or within 2 standard deviations. And 99.7 of the area under the curve is within 3 standard deviations. So here, if you go only from here, if you draw there a vertical line and draw here another vertical one, then the total area under this curve is set to be 68%. If it is within 2 standard deviations away, then the area, everything here under the curve, is 95%. And if you go from -3 to 3, or 3 standard deviations away from the mean, then the total area there under the curve is 99.7%. And if you could see, we still have 0.3%, and that 0.3% is in fact divided equally in these two smaller endings here. That's why the areas that are not within 3 standard deviations away would represent only, that are either going to the left or either going to the right. The total of that is just 0.3% in all, which is quite negligible or a very small probability. Let's have the following example. The Wechsler Adult Intelligence Scores, normally distributed with the population mean of 100 and a population standard deviation of 15. We have this notation. This notation actually indicates that you have a normal distribution with 100 as a mean and 15 as standard deviation. This is in fact a notation. So for that, it means to say that 68% of the scores are within mu plus minus your standard deviation. Remember, your mu is 100. So if you subtract it by 15, 100 minus 15, that's 85. Then to get the higher one, you add 15. 100 plus 15, you get 115. Which means to say that approximately 68% of the scores are within 85 to 115. If you have two standard deviations away from the mean, then you have 100 minus 2 times 15, which is 30. So that's 70. 100 plus 2 times 15. 2 times 15 is 30. 100 plus 30 is 130. This means to say that around 95% of the scores ranges from 70 until 130. And lastly, if you have 3 standard deviations away from the mean, then you will subtract the standard deviation thrice and add it thrice as well to determine the range of values. So if you wish, 100, you subtract it thrice, minus 15, minus 15, minus 15, that's 45. 100 minus 45 will give you 55. And you will add also 3 times 15, which is 45. 100 plus 45, it's 145. This means to show that those people who got 55 to 145, it is expected that there are 99.7% of them. Again, assuming that they follow a normal distribution. So this is it. This is how it looks like. So from here, you subtract by 15, 85, minus 15, 70, minus 15, 55. Plus 15, if you go to the right, 115, 130, 145. So 68% here, have you see, are 85 to 115. 95%, 70 to 130. And from 55 to 145, approximately 99.7% of them. I hope it's clear with us. Now, let's talk also about the symmetry in the tails. Because the normal curve is symmetrical and the total area under the curve, or AUC, is exactly 1, we can easily determine the area under the curve in the tails as well. For example, if we are talking about 95% here, so it's 2 standard deviations away, right? If you could still recall. So here, from 70 to 130, that's 2 standard deviations away from the mean. So that area under this curve is 95% based on the rule I gave earlier. So if it's 95% here, then remember the total probability is 100%. And so subtract it by 95. So you have 100% minus 95%, that's 5%. But since these two tails here are actually symmetrical with one another, there's also symmetry. It means to say that the areas in these two are in fact equal as well. That's why 5% divided by 2, you get 2.5% here. This means to say that 2.5% of the people there have scores or have scores below 70, whereas the remaining 2.5% also have scores that are higher than 130. Let's talk about male heights. For example, you have male heights that represent a normal distribution with a mean of 70 and a standard deviation of 2.8. So if we talk about within 1 standard deviation away, So of course, from 70, you subtract by the standard deviation. 70 minus 2.8, that gives you 67.2. From here, 70 plus 2.8, that gives you 72.8. And according to the rule we discussed earlier, to the empirical rule, 64% of the scores, or 68% of them, should lie between one standard deviation away from the mean. That's why it is expected that 68% of them are within 67.2 and 72.8. So what does this mean then? Since this is perfectly symmetrical and that the total probability under this curve is 100%, then 100 minus 64, or sorry, it should be 68% there. I think it's wrong here. Please note, this should be 68%. Thank you. That's why if you have 100 minus 68, that is in fact 32%. But since these two tails here, both going to the left and both going to the right, are symmetrical, so this 32 will be divided into 2. So that's why you have 16% each of these tails. So 16% of the areas, or of all the scores, are below 67.2, whereas 16% also of all the heights are above 72 or higher than 72.8. That is because of symmetry. Okay? By the way, the heights here and standard deviations are in terms of inches. Moving on. If you could still recall in our first discussion, we have two branches of statistics. One, it's what we call your descriptive statistics. This involves the organization, summarization, and display of data. Like if you are utilizing frequencies, ranks, measures of central tendencies, measures of variability, percents or percentages, that's descriptive. But we have also discussed another one, which is what we call inferential. This involves using a sample to draw conclusions about your population. And so from this point forward, our focus is not only descriptive, but rather inferential. Like, given a certain data set, what possible conclusions can we form out of them? What possible inferences, what possible generalizations could be formed out of the data that we have? Speaking about inferential statistics, it allows conclusions about the population to be generated from sample data. It is applicable when probability sampling is used. And that's why, if you could see, if we have probability sampling, just like the one that we mentioned last time, remember, if you have your random sampling, your simple random sampling, like your fishbowl or your lottery method, your systematic sampling, your stratified random sampling, your cluster sampling, what else? And we have your multi-stage sampling. That's why it's really applicable when probability sampling is used. Inferential statistics is founded on the theories of probability. Results are questionable when non-probability sampling is used. That is why it is very important that you know what sampling technique you utilized, because later on it might have an impact or it might affect the type of generalization or conclusion that you could get from your data. And the branches of inferential statistics are the following. So we have here, in doing inferential statistics, you could do either hypothesis testing or estimation. When we speak about estimation process, you could estimate either using a point or you could give either a point or an interval estimate. We will discuss it later on. And aside from estimation, you could also have what we call hypothesis testing. This includes parametric and non-parametric statistics whenever it is applicable. Okay? Now, it is important to determine an appropriate inferential statistical test of hypothesis. So, if you could see here in this diagram, there are actually many ways of determining. So it's like there's some sort of a diagram or a flow chart on what to do. And the level of measurement is an important indicator in the choice of statistical hypothesis testing procedure. Is your dependent variable nominal, ordinal, interval, or ratio? It's important that you know them because it would actually help you to determine what particular statistical tools or techniques are applicable. Also, parametric tests have more stringent assumptions before they can be used. Data must be at least interval, and the distribution of the data must be normal or approximately normal. In reality, having a perfect normal distribution is most likely impossible. But however, it could be approaching normal or approximately normal, but perfectly normal, not that much. And we also discussed last time the concept of populations and samples. So let's have a quick review. When we speak about the population, it is the complete set of individuals. It is a characteristic. Okay, when we speak about the complete set of individuals, it is not correct to say that all people in the world, that's your population. No. Your population is in fact dependent on the type of study you are pursuing. That's why it is important that you know who your target population is. You should know the characteristics of your target population, who is included in the population, what are their defining characteristics. And a characteristic of a population is what you call parameter. That's why if you would compute, for example, the mean and standard deviation of a population, what you have computed is a characteristic that is an example of what we call parameter. Sample, on the other hand, is a subset of the population. When we speak about subset, it is only a portion of your population. Like, you do not take everyone, you just take only, say, some of them, then you have taken a sample. And a characteristic is called, a characteristic that you compute or you take from the sample is what you call statistic. Take note, no S, statistic. In most cases, we cannot study all members of the population. Why is that so? Because usually, if the population is too large, for example, then you would need a lot of time, money, effort, energy to gather data from them. However, if you resorted to getting a sufficient number of samples from the population, from your target population, and if your sample is indeed representative, then what is true for the sample may most likely be true for your population. Again, assuming that the sample is representative. If not, then you cannot do such. And so here are some concepts. We want to learn about population parameters. So we wanted to learn about the characteristics of your population. And so what we do is we do some sort of random selection using those random techniques or random or probability sampling techniques, for example, that we discussed last time. So you could utilize whichever is applicable. And after doing some sort of random selection, you arrive to your smaller sample, to your sample. And out of these samples that you have, you would be computing your statistic. For example, your sample mean. And the thing is, if you computed the sample mean, and if these samples are indeed representatives of your population, then then the sample mean could be used to approximate the population mean. Again, as what I mentioned earlier, if your sampling is adequate and it was done properly, then probably the sample mean could approximate the population mean. That's why you are making inferences. Like what is true for the sample may be true for the population. However, we have to note that in reality, the sample mean and population mean are rarely equal. It's just that probably it could approximate, your sample mean could approximate population mean in some scenarios. Statistical inference is the act of generalizing from a sample to a population with calculated degree of certainty. So from your population, you have to get a parameter. From your sample, you have to get a statistic. But hopefully, with representativeness of your sample mean could also be used to generalize something about the population parameter. Now, let's talk about parameter and statistic further. It is essential that we draw distinctions between a parameter and statistic. Parameters are numerical descriptions of a population characteristics. That's why parameter is computed from the population, and examples of that is your population mean and population standard deviation. And when we speak about statistic, it is a numerical description of a sample characteristic. That's why remember that your sample is, that your statistic is taken from the sample. And we have here your population, your sample mean and your sample standard deviation as well. And so that you won't get confused, always remember that they begin with the same letter. Parameter, population. They both begin with P. And we have statistic, sample. They both begin with S. This is to show that parameters were taken from a population, whereas a statistic is taken from a sample. Sir, you might ask, sir, how about statistics with S? That term, statistics, could also be the plural of statistic. That is, statistics would mean that there are two or more statistics. Okay, I hope it's clear with us. Okay, let's have this one. Decide whether the numerical value describes a population parameter or a sample statistic. How about this? A recent survey of a sample of 450 college students reported that the average weekly income for students is $325. Is this $325?
parameter or statistic. And this is statistic. Why? Because the average of $325 is based on a sample. And since it is taken from a sample, then that computation or that value is an example of a sample statistic. All right? Letter B. The average weekly income for all students is $405. What do you think? This is already a parameter. Why? Because it says there for all students. That's why this is a parameter. So you have to be very careful. Once population is given, that's parameter. But once sample is given, then that is statistic. Now, let us speak or talk about point estimation and interval estimation. So the thing is point estimation and interval estimation the same? We'll find out. Now, recall earlier of this one. Remember, if you are doing random selection, every member of the population has the same chance or equal chances of being selected to be part of your sample. And in fact, your sample mean could be used to estimate about the population mean. Now, this time, let's talk about statistical estimation. So we have here first the point estimate. When we say point estimate, a single value is given as an estimate of a parameter of a population. And a sample mean is a point estimate of your population mean. This is such because, as what I have mentioned again, whatever you could deduce from the sample may be deduced for the population, provided that representativeness is satisfied. So for example, you found out that the average weekly income of the students is $400. Or let's say in the Philippine context, let's say you found out that the average daily weekly allowance is 800 pesos. So that is an example of a point estimate. It's a single number. However, if you have here your interval estimate, an interval within which the value of a parameter of a population has a stated probability of occurring. And always remember that a point estimate is always within the interval estimate. For example, if your mean is 800 pesos, but suppose that you would, if someone would guess the mean or the actual mean or the actual parameter or actual statistics, for example, then they would say probably the allowance is between 700 to 1,000. So that is some sort of an interval estimate. So if you could say the actual mean allowance is 800, that's point estimate. But if you could say, oh, maybe the actual allowance is between 700 to 1,000, that's interval estimate. I hope I have made this distinction. This time, let's go with hypothesis testing. Okay? Let's talk about statistical inference and the role of chance here. And so if you have your scientific knowledge, scientific knowledge could actually lead one to develop his own reasoning and intuition. And if not, scientific knowledge could actually be derived by means of empirical observations. Like you perform experiments, you perform your own study, you perform your own data gathering to verify something or to establish something. And in doing reason, if you have your reason and intuition, you have sometimes, if you don't have results yet, then all you have to do is formulate your hypothesis. When we speak about hypothesis, this is an educated guess. It's educated considering that it is actually based on certain laws, principles, theories. And if you would do, for example, your empirical observations, for something to be empirical, it must be supported by data. That is why you would collect data to test your hypothesis. There are instances as well where you would formulate your hypothesis and test them. And after testing, you may also form other hypotheses about your data or whenever needed or necessary. And remember, for here, if you formulate hypothesis, then you have to collect data to test your hypothesis and make sure that the collected data is sufficient enough for you to run certain hypothesis testings, which would actually tell you to either reject or not reject your hypothesis, depending on what it says. And remember that if you reject or not reject your hypothesis, this might be attributed to chances. Chances are maybe your data is not adequate. Probably if your data is too small, probably you have not collected enough data. Maybe the data you collected is not correct. So there are so many things that could affect either if you would really reject or not your hypothesis, and depending also on the results. Random error could happen. So random error or could be due to chance, which could actually be controlled by statistical significance or by confidence intervals. And the thing is, note that systematic error could actually happen in the data collection process. So make sure that you collect well using sound principles, especially as much as possible by means of random sampling techniques. Now, when we speak, let's talk about testing of hypothesis. When we say hypothesis testing, it is a decision-making process for evaluating claims about your population. And a statistical hypothesis is in fact a conjecture or a guesswork about a population parameter. This conjecture may or may not be true at all. That is why there are times where you need to reject or not reject your hypothesis depending on the results. Now, we have two types of hypothesis. The first one is what you call null hypothesis. And in the null hypothesis, if you could see more often in some journals or in some studies, they would say it would claim, it is actually saying that there is no difference. For example, like there is no significant, if you see like there is no significant difference between the test scores of the two sections. There is no significant difference in the pre-test and post-test scores. If they would say there is no significant relationship between height and weight of a person. So that's an example of your null hypothesis. And it's symbolized by HO. And it is a statistical hypothesis that is actually being tested and that is hoped to be rejected whenever possible. For example, the population mean value is equal to a certain hypothesized standard value. For example, your claim is the population, the height of students is 5'5". So if your null hypothesis could be like that, there is no significant difference between the two parameters. Or you could say there is no significant relationship between the two variables, and so on. And remember, if there's no significant difference, then we could say that the two population parameters, for example, are equal with one another, or that the hypothesized value is indeed equal to the collected value, or similar to that. How about alternative hypothesis? It is in fact the question being explored by the investigator, and in some books they call it HA, some books call it H1, but both of them represent alternative hypothesis. It is a statistical hypothesis that is reported when the null hypothesis is rejected. So take note, you report this one if you reject the null hypothesis. If you don't reject the null hypothesis, of course, you will report the null hypothesis. Examples. The population mean value is greater than, less than, or not equal to a certain hypothesized standard value. For example, a certain study claims that the mean population of students is 5'5". Your alternative hypothesis could be the mean height of students is not 5'5". That there is a significant difference between the two parameters. For example, there's a significant difference in the weights of men and women. Or you could say that there is a significant relationship between two variables. Like there is a significant relationship between height and weight. So this is your alternative hypothesis. And note, statistical methods are used to test hypotheses. The null hypothesis is the basis for statistical tests. Remember this. The null hypothesis is the basis. If you don't reject the null, you report the null hypothesis. If you reject the null hypothesis, you have to report the alternative hypothesis. Let's have an example. I would like you to state the null and alternative hypothesis of each of the following. 1. A researcher thinks that if expectant mothers use vitamin pills, the birth weight of the babies will increase. The average birth weight of the population is 6.2 pounds. So you see, the average birth weight of the population is 6.2 pounds. This is an example of what you call point estimate. But let's formulate now our hypothesis. But before that, our variable x is the birth weight of babies in pounds. The parameter being tested here is the population mean for this case. The null hypothesis could be the average birth weight of babies is 6.2 pounds. So you are denying that there is a significant difference. So if there's no significant, you could also say, in this case, that since they do not differ, that's why you treated them to be equal to your hypothesized point estimate. That's why this is your null hypothesis. The average birth weight of babies is 6.2 pounds. For your alternative hypothesis, which is HA or H1, of course, for null hypothesis, if it is equal, your alternative hypothesis is greater than here. How the average birth weight of babies is greater than 6.2 pounds. You might ask, sir, what is your basis for saying greater than 6.2 pounds? The basis is the given here. It says that if expectant mothers use vitamin pills, the birth weight of the babies will increase. Increase implies that it will be greater than. That's why that is our alternative hypothesis. I hope it's clear with you. You could say it's also is higher than 6.2 pounds. That's still correct. So it's important as well that we know the proper terminologies for such. No? Number 2, an engineer hypothesizes that the mean number of defects can be decreased in the manufacturing process of CDs using robots instead of humans for certain tasks. The mean number of defective CDs per 1,000 is 18. So still, we have here another point estimate, because the problem here or the example is claiming that the mean number of defective CDs out of 1,000 is 18. So your variable here will be the number of defective CDs. The parameter being tested is the population mean. The null hypothesis is your HO. The mean number of defective CDs per 1,000 is 18. You do such because you stick with what the literature or with what it's the product of what the situation is saying, and you do not deviate from it. But how about your alternative hypothesis? It says here can be decreased if using robots, if you use robots. So if there is the word decrease, what particular word or symbol or should we place as part of your alternative hypothesis? That would be the mean number of defective CDs per 1,000 is less than 18. Why less than 18? Because of the term decreased. So I believe that the term less than is appropriate for this scenario. I hope you got it. If you wish, you could also write the null and alternative hypothesis in symbol form. For example, you could write here, your HO could be, your population mean is 18 CDs. And for your HA, because it's less than, your H1 is mu is less than 18 CDs. It's okay here. However, remember this, if you will be doing research, particularly in your thesis, for your thesis, most likely you will be using the words, this version, rather than the second version. But at least you know that it could be written in symbolic format. Okay? Number 3. A psychologist feels that playing soft music during a test will change the results of the test. She is not sure whether the test scores will be higher or lower. In the past, the mean of the scores was 73. So what is our variable here? It is your test scores of students. And our parameter being tested is the population mean, or your mu. What will be our null hypothesis? That we will stick to that 73, right? So our null hypothesis is that the grades will be the same, or the mean of the test scores is 73. There are many ways of writing your null hypothesis, so you just choose one that fits your taste, as long as you do not deviate from the main essence of the situation. For your alternative hypothesis, or your H1, what should we write? Should we write greater than or less than? Take a look here. In the second sentence, the psychologist is saying that she is not sure whether the test scores will be higher or lower. It could have a tendency to be greater than or less than, right? So if that is the case, you are not sure if it's greater than or less than, so it's better to say the grades will not be the same, or you could say that the mean of the test scores is not 73. All right? Or you could say the mean of the test scores is not equal to 73. That is also correct.
And so, if you could see from here, we could have here a summary of one and two-tailed tests. The alternative hypothesis determines whether the test is in fact one-sided or two-sided. In the first example I gave you, your alternative hypothesis was that your population mean is greater than 6.2 pounds. This is an example of a one-sided or one-tailed tests. Like here, for this one, greater than here. So for example, you are actually claiming that it's not within this one and probably the mean is located around here. So it's a one-tailed test, particularly a right-tailed test, because the value that you might possibly get or that you are trying to test might be indeed be found at the right or is greater than the hypothesized value. That was for the first given. For the second given, we mentioned earlier that the population mean is less than 18 CDs. And it's one-sided. It's one-sided as well because less than only, it's only found on the one side and it's also one-tailed. And the second one here, it's also a one-tailed, entails a one-tailed test or a left-tailed test, because if it's something that's less than your hypothesized value, then it might be found here at the left end of your normal curve. So here you have this if mu is less than your hypothesized mean. However, if you would take a look at the third given I gave you earlier, I mentioned that mu is not equal to 73 points. And when we speak about not equal to, the value that you might get, if it's an extreme value, may be found either at the leftmost, at the left, or at the right. That is why this entails a two-tailed test, or a two-sided or a two-tailed statistical. It would entail two-sided or two-tailed tests later on, which could be found here. So it's also important that you know what you are looking for if it really entails a one or two-sided or one or two-tailed tests. And what will be your basis for such? Probably you could consult literature. Ask or check what literature is saying for you to decide if you need a one-tailed or two-tailed tests. Let's talk about one-tailed tests in our types of hypothesis testing. In a one-tailed test, it is a directional test with the region of rejection lying on either left or right of the normal curve. It is used if the scientific hypothesis predicts a direction of the result. So if the sample mean falls in this area, we can reject the null hypothesis. So these shaded areas here are what we call the rejection region. And these non-shaded areas for these cases would refer to your non-rejection region. In a right-tailed test, the alternative hypothesis uses comparatives such as greater than, superior to, and their other counterparts or their other synonyms. And if you have a left-tailed test, your alternative hypothesis uses comparatives such as less than, below, lower, and so on. But note, literature is the basis here. And for two-tailed tests, it is a directional test with a region of rejection lying on both sides of your normal curve. That's why if you have here your alpha, for example, since it's just one region, so alpha will be placed entirely there. It's either placed entirely at the right or at the left of your normal curve. However, if you have a two-tailed test, you are actually acknowledging the fact that the extreme results may be found or might be found on the extreme left or on the extreme right. Your rejection region could be found here or here. That's why your alpha was divided into two. So this is 1/2 alpha and this is also 1/2 alpha, because as what we mentioned also earlier, these two regions at the tails, at the ends, are symmetric with one another as well. If the sample mean falls in either of these areas, we can reject the null hypothesis. Okay? I hope it's clear. Now, humans as we are, sometimes we commit errors. Sometimes we commit mistakes in decision making. A statistical test uses the data obtained from a sample to make a decision about whether the null hypothesis should be rejected or not. For example, if this is your decision on the null hypothesis, either you reject it or not. And if we speak about the true nature of your hypothesis, if it is true or false. If you reject a true null hypothesis, you committed what we call a type 1 error. Type 1 error occurs if the null hypothesis is rejected, even though if it's true. Type 1 error happens when you reject a true null hypothesis. However, if your null hypothesis is false and you rejected that, that is in fact a correct decision, because we are supposed to reject something that is false. If your null hypothesis is true and you did not reject it, that is in fact a correct decision. However, if your null hypothesis is false, but still did not reject it, you committed an error, which is what we call a type 2 error. Type 2 error occurs when the null hypothesis is not rejected, even though it's false. Okay? So to know more about this, let's have the following. For example, you are a doctor. This guy is a doctor, and he is talking to a male patient. Let's say your null hypothesis is you are not pregnant. And for the first scenario, for the type 1 error, your null hypothesis is true, right? That this guy is not pregnant. But he rejected it and he told this guy, "Sir, you are pregnant." That is a type 1 error. Or in some books, they call it a false positive. You committed a type 1 error or a false positive error. However, if you say that you are not pregnant and the null hypothesis is false, so then you rejected it, then that's a correct outcome. Also, the null hypothesis here is true, but you did not reject it, so it's still a good one. We have a true positive and a true negative. That's okay. However, for the second scenario, this woman is really pregnant. And the doctor told her, you're not pregnant, even though she is. So if you could see, the null hypothesis is false, but in this doctor did not reject it. So she committed a type 2 error. Type 1 error, type 2 error. So this is just an example. Note that when there is a large difference between the mean obtained from the sample and the hypothesized mean, then the null hypothesis is probably not true. For example, according to your literature, the mean height is 5'5". If, for example, you found out that the mean height is 5'6", so probably it's kind of near. So most likely, your null hypothesis is true. But if your example, if your literature is saying that the mean height of people is 5'5", and you found out that the mean height is 7 feet, then I think it's kind of far. So probably the null hypothesis is most likely false. But again, for our class, it is not the researcher who decides alone. The researcher should be guided with the results of statistical computations. Now, let's talk about significance level. Speaking about significance level, let us denote it with alpha. This Greek letter alpha, it is the probability of rejecting a true null hypothesis. And also, significance level is the probability of committing a type 1 error. And remember that since probability, we are talking about probability, so it should range from 0 to 1 as well. To illustrate my point, the most commonly used alpha in research is 0.05. And what does this mean? The probability of rejecting a true null hypothesis is 5%. Why 5%? Because this is decimal. If you convert a decimal to percent, you will multiply it by 100 and attach the percent sign, or simply move the decimal point 2 places to the right and attach the percent symbol. And also, it could also mean that the probability of committing a type 1 error is 5%. That's what it meant. So in this case, you are allowing a 5% error. And if you are allowing 5% error, then how confident are you that you will be making a good decision? That would be 100 minus 5%, which is 95%. That's what we meant here of alpha, which is 0.05. Now try this. What does an alpha of 0.01 indicate? It means if you convert 0.01 to percent, you move the decimal point to the right 2 times and attach the percent symbol. So you get 1%, right? This means the probability of rejecting a true null hypothesis is 1%. Or it could mean that the probability of committing a type 1 error is 1%. So what have you noticed if you decrease your alpha? So I mean, but before we answer that question, if you will most likely commit a type 1, the probability of committing a type 1 error is 1%. How confident are you that you will be making a good decision whether to reject or not the null hypothesis? It would be 100 minus 1, or 99%. So you will have 99% confidence. Okay, I hope you got it.
So normally we are using 0.05. Sometimes others would use 0.01. Some studies use different alpha or different significance levels. Some are using 0.1. 0.1, that's 10%. It could be used sometimes in agriculture, sometimes. And some studies use 0.01 or 0.001. And in this case, these are actually used in certain studies wherein human lives are involved. For example, let's say in medical fields or in medicine. There are some studies that in medicine that use 0.05. There are some that use a lower alpha, whichever is necessary or is needed. Now, how about the p-value? It is the probability of getting a more extreme value than the one you got from the experiment. This value could actually be determined using software such as SPSS, which we will be having next time. So p-value in our class, remember this, the p or the probability value. In our class and in research as well, we will express p in 3 decimal places. Other values could be expressed in 2 decimal places, but p will be in 3 decimal places. In SPSS, or the statistical package for the social sciences software, the p-value appears as either sig or sig two-tailed, depending on the type of statistical test you are running. For example, if you could see this one, this is an example of a statistical table that was derived using t-test for independent samples. This is your sig two-tailed. If you see here your sig two-tailed, this is the p value that we are looking for. Okay? Now, let's talk about statistical significance. Let's talk about the concept of critical value. That critical value separates the critical or rejection region from the non-critical. In some books, they call it acceptance region, but some authors do not use the term acceptance. They use the term non-rejection, designated by CV. The critical or the rejection region here are denoted in red, denoted here or shaded here in red, covers the range of values of the test value that indicates that there is a significant difference and that the null hypothesis should be rejected. Later on, if the p-value or if the computed value, for example, is here, then you have to reject the null hypothesis and report the alternative hypothesis. However, if you see here, we have alpha as your we have your alpha earlier as your significance level. Since we have two-tailed tests for this case, so alpha was divided into 2. We have alpha over 2 here, and we have alpha over 2 as well. And since the total sum of all probabilities here is 1, then the probability that a certain value might fall here is 1 minus your significance level alpha, or simply 1 minus alpha. The non-critical or non-rejection region covers the range of values of the test value that indicates the difference was probably due to chance and that the null hypothesis should not be rejected. So if once it falls here, do not reject HO. Now, speaking about your level of significance, the maximum probability of committing a type 1 error is designated by alpha, and an alpha level of 0.05 is reasonable and widely accepted by many scientists. But again, there might be instances that you have to use a different alpha depending on the suggestion of your panel or of your statistician. If the p-value is less than or equal to the specified significance value or to the significance level alpha, the null hypothesis is rejected. Otherwise, the null hypothesis is not rejected. Okay? So remember this. So here is a guide, an easy one. So if the computed p-value is less than or equal to alpha, reject the null hypothesis. And if you reject the null hypothesis, what will you report? You will report and interpret the alternative hypothesis. So that is if p is less than or equal to alpha. If you reported the null hypothesis instead of the alternative hypothesis for this case, what error have you committed? Did you commit type 1 or type 2 error? You committed a type 2 or beta error. I forgot to introduce this one earlier, but beta error, BETA, beta error, is also the other term for type 2 error. How about if the computed p-value is greater than your alpha? You will do not reject HO for this case. So you don't reject HO or your null hypothesis. And if you don't reject the null hypothesis, you will report it as well. So if P is greater than alpha, you have to report and interpret the null hypothesis. For this case, if you reported the alternative instead of the null, what error have you committed? You committed a type 1 or alpha error. So you have to be very careful. Alpha error is also the other term for type 1 error. Now, the thing is, if I'm going to ask you, which error is worse than the other? Is type 1 or type 2? And believe it or not, many statisticians would agree that type 1 error is worse than type 2 error. So you have to be very careful about it. Now, if we are going to test our hypothesis, your confidence interval and significance level tests here. So it's 95% here. Then if your alpha is 0.05, that's why it's 95% here in the middle. And then here we have 2.5% and we have here 2.5% as well. We have the lower limit and we have here the upper limit. A value for null hypothesis is within the 95% confidence interval here, and having a p-value of 0.05, a p-value greater than 0.05 are in fact interchangeably the same. And a value for null hypothesis outside of 95% of the confidence interval, meaning to say it's either found at the extreme left or at the extreme right here, indicates that your p-value is less than 0.05, and these two are in fact interchangeable. They mean one means the other, and the other means the first means the second, and the second also means or indicates the second, this one here. Here, the null hypothesis is accepted. However, some authors don't use the term accepted. They use the term null hypothesis is not rejected. Here, if p-value is less than 0.05, the null hypothesis is rejected. Now, we will talk about the steps in conducting hypothesis testing. Disclaimer here, the steps that I will be presenting to you are only specific for this class. if you consult literature, their steps are different. Some use only 5 steps, some use 6 steps, some use 7 steps, depending also on the author or on the institution. For my case, however, I will be adapting 8 steps. The first one is state the problem. You state the null and alternative hypothesis. I would like you to state the significance level or alpha. For our class, we will be stating it as 0.05 only. For number 4, we will state the test statistic. We will state your decision rule. The test statistic, it could either be t-test, ANOVA, depending on what is applicable or what is best for the data. Number 5, you state the decision rule. You compute for test statistic and state decision after which, and lastly, to formulate your conclusion. Take note that it's quite lengthy. I have 8 here for this class. So that my purpose here or intention is that you could see that's how it's done. At least you see it step by step, that there is a linearity in reasoning from 1 to 8. Let's talk also about parametric versus non-parametric statistics. So you might heard of this one. And when we see in parametric statistics, the information about the distribution of the population is known and is based on a fixed set of parameters. In non-parametric statistics, the information about the distribution of a population is unknown and the parameters are not fixed. So they may change or dependent, which makes it necessary to test the hypothesis for the population. Parametric statistics assume that the sample data follows a probability distribution that is based on a set of parameters. The most common assumption here is that the data is distributed normally or it follows the normal distribution curve, which I gave you earlier. Most of the common statistical methods are parametric. Although parametric statistics are considered more powerful than non-parametric statistics in terms of generalizability, they are not always applicable for the analysis of the significance of differences. Why? Because some of the assumptions of parametric tests have to be, assumptions of parametric tests have to be satisfied before we use them. If not, we may resort to non-parametric statistics. All right, that's why parametric statistics have more stringent assumptions than non-parametric statistics. So here are, for parametric tests, assumptions have to be met. According to Field 2009, it should be normally distributed as much as possible. There should be homogeneity of variances. Data measured is at least interval scale, particularly your dependent variable. There should be random independent sample or sampling. So it's quite assumed here that one can do random sampling techniques, although there are instances wherein others use parametric statistics even without using probability sampling techniques. And there should be no outliers here. When we say outliers, these are extreme scores, whether extremely high or extremely low scores. Non-parametric tests are assumption-free tests. And some of the assumptions, according to Field 2009, don't require data to follow a normal distribution. So normally distributed or not, if it follows a normal curve or not, it may be used. There should be independent random samples. The measures are at least on ordinal scale.
in most of the tests. So it could be your dependent variable could either be ordinal, interval, or ratio, but not nominal for this case. Expected frequency in 2x2 tables should be at least 10, and in other tables, at least 5. And of course, you have to test dependent assumptions. And here are some of them also in relation to this one. We also have particular literature which could be used to substantiate or say more about this one. And please, you may read them on your own. So for now, here is about your parametric and non-parametric tests. We will be learning more about them next time. Here are some differences between parametric and non-parametric statistical tools. In parametric, population is well known, but for non-parametric, no information about the population available. There are assumptions made about the population, like the population mean and standard deviation. For non-parametric, no assumptions were made about the population. In parametric, sample data is based on the normal distribution, but for non-parametric, it's simply arbitrary. Applicable parametric statistics are applicable for continuous variables. When we say continuous, it should be either be interval or ratio. Your dependent variables have to be interval or ratio. Do not use parametric statistics if you have nominal or ordinal dependent variables. Whereas for non-parametric statistics, it's applicable for continuous and discrete variables. So here, ordinal, interval, ratio are okay. Nominal depends, it could be as well. And parametric statistics are more powerful generally than non-parametric statistics in terms of generalizability, in terms of making generalizations or inferences. With that, I hope you learned something from this video. Thank you so much and a great day to one and all.